So now guys, we are going to talk about matrix factorization. So that is a problem. So we have discussed already about how user collaborative filtering works, how item collaborative filtering works, and all of those are very awesome techniques. And now we are going to talk about something that is very crucial. This is also collaborative filtering. This is also collaborative filtering for item collaborative filtering. But there's an interesting concept that we are going to talk about right now, which is called a single value decomposition method, which is basically a type of matrix decomposition method, matrix factorization. So what is this matrix factorization method, right? Before we kind of get into this, let's kind of get an understanding of why we are doing this. Second, get an intuitive idea of what we are trying to do, right? So what are we trying to do with case of matrix factorizations? In case of matrix factorization, the understanding is this, that why we are doing that. First, let's understand that. So we have user U1, U2, U3, and we saw that there were a lot of movies which were basically sparse, right? So in our first problem, the reason why we are trying to look at a matrix factorization method is basically we would have all of this till m1000, right? And this is basically something, there are a lot of sparse values, right? So there are a lot of blank values, right, all over through the matrix. So because there are a lot of blank values, the problem becomes is that calculating all of those things, like say calculating correlation, distances and all of those, this becomes a huge problem if you have a lot of sparse matrices. And that's why you remember the reason why we had to kind of take movies only which are greater than 100 ratings, right? The reason why we had to do all of those. Because if there are sparse ratings, if you do kind of take a correlation and try and do the distance calculation, well, it can really go very bad, right? So that's why we need to kind of take care of the sparsity very well. So one way we did was basically kind of just take movies which have greater than 100 ratings. Well, that's one good way, but not necessary, because if you do that, you're just gonna again limit yourself to the 100 movies, right? So to counter that, what do we do? How do we kind of tackle the sparsity problem? So one way is basically that instead of having 1000 columns here, what if we can have, say, instead of this 1000 rows, what if we can have it, say, in 20 columns, right? In 20 columns, if we kind of compress this data, right, there is a lot of sparse data. If we can compress this data in say 20 columns, that would probably make a lot more sense, right? Because then it would not be as probably sparse as possible, right? The way there are probably 1000 movies, a user one has probably not seen, say, 1000 out of 1000, he has probably not seen 800 or 600 of those movies. Now if we kind of, and that basically gives us 200, 600 columns, so 600 sparse columns, right? 600 blank columns. Instead of doing kind of relying on those kind of movie matrices, movie columns, if we can have some kind of other columns which basically can compress the sparsity down, then first we would have low sparsity, right? The sparsity problem would be somehow solved if we can compress this this number of columns into a lower number of columns. Now how do we do that, and what is the intuition of these columns that we are representing? The understanding is very simple. What we are trying to do is an intuitive idea. What we are trying to do is we are trying to represent a bunch of movies using something called a genre, right? For example, genre for movies could be comedy, thriller, adventure movie, biopic, and all of those sorts, right? So underlying assumption is that we do not know explicitly what are the genres. We could, in real life we could, and we could use that also, but the understanding here is that based on how users have rated movies, right? So basically the understanding is that if two movies are extremely similar, right, as in they have been rated, so if there's probably movies which are extremely similar to each other, right, so that means probably they belong to the same genre, right? When I'm saying very similar to each other, that means basically there are users who either like them or who hate them, right? So they're both either liked by an user or they're either hated by an user, right? So those are the kind of cases where we are saying two movies are similar. So if basically there are a couple of bunches of movies which are very similar to each other, then we can club all of them in a particular genre, right? So then this genre represents movies which belong to one particular genre. And I'm not using the actual genre of the movie to kind of infer this. I'm basically kind of inferring this from the idea of how movies are rated by different users, right? So based on ratings of users, if I can figure out which are movies which are similar to each other, I can basically say that they are belonging to one genre. And then based on this, I can kind of compute this different genres in the movies. So in this case, we'll basically have the same number of users, but in columns, instead of having 1000 columns, we would basically have 20 or so columns, right? And those columns would basically represent the different genres. And this is exactly the concept of matrix factorization and SVD that we are going to discuss right now. So before we kind of get into how do we do all of that, first let's understand what is matrix factorization. Matrix factorization is nothing but breaking a matrix into different components, right? So this is the matrix that we want to break. So this is the matrix of user cross ratings, right? So the user cross ratings is called the R matrix. So this has got whatever number of users, say this has got 100 users, right? So 100 cross 1000 rows, right? So 100 cross 1000 is the size, and this is the one that we want to break into different parts. Now why do we want to break into different parts? What are the different parts? Let's understand that. So what is singular value decomposition? Singular value decomposition is an algorithm that decomposes a matrix R into its best lower matrix, lower rank, right? So what is rank and all of this, I would request you to kind of go and have a look into what rank of a matrix means. Mathematically decomposing R into two unitary matrix and one diagonal matrix. So there's this matrix U and V, which are basically unitary matrices, and there's this diagonal matrix sigma. So what is sigma? So let's obviously, what this part of the slides basically says that there's an algorithm which can basically decompose your R matrix into two component matrix, right? So there would be 100 into 20. There's one matrix that is U. Then there is sigma, which is 20 cross 20 cross 20, and then there is V, which is 20 VT, which is basically 20 cross 1000, right? So this is the idea of breaking matrices. So this matrix is basically this matrix, right? So this matrix that you have users and the genres is called the U matrix. Then the sigma matrix is basically a diagonal matrix which has all the 20 genres cross 20 genres. And then there's one matrix which basically maps each genre to the corresponding movie, right? So V basically composes of different genres, G1, G2, and the movies, right? Movie M1, M2. It basically says that what is the component of genre 1 in movie 1, right? And what is the component of genre 2 in movie 2. And for each movie, what is the composition of different genres. So that is a matrix that is called V, right? So that is V transpose. V is basically the transpose of this matrix. So that's the understanding of what SVD does, right? So conceptually, this is a matrix U. 20 cross 20 is a diagonal matrix. We'll understand that you can kind of look into SVD to understand what this 20 cross 20 matrix intuitively means. And then V is basically this matrix of genres cross movies, right? So U cross genres, users cross genres is your U, V and D, right? So and this is what your SVD tries to break your matrices into. So once you break them out into three different matrices, then it's very simple, right? So then you can basically figure out which users are very similar to each other based on genres, and from that you can kind of, once you figure out that user 1 and user 2 is, for user 1 you basically figure out that yeah, he's probably more likely to like movies from one particular genre. You then say that hey, from this genre these are the different movies that are there, you can probably recommend these movies to him, right? So it's much more easier to figure out which genre a user likes rather than trying to figure out which movies a user would like, right? Because it's a much smaller compact matrix and calculating correlation, all of those are much easier, right? But then there's obviously we want to making predictions. Conceptually, intuitively, that is what it is doing. Now let's understand what we are going to just have also look into how the algorithm functions. So this is the first part, which is where we kind of calculate this is a user rating matrix we are familiar with. Then what we do is we normalize all the values because normalizing is, without normalization it might not work very well, and it for sure would not work very well. That's one of the assumptions of matrix factorization methods. So we first basically fill all the NaN values with 0. Once we do that, then we calculate the matrices of what are the different mean values of each of the user rows, and then we subtract that, right? And once we subtract that, then we basically do this SVDS, which is basically the way to kind of which is the algorithm which is already there in SciPy and NumPy. You can directly use that to break your matrix norm. Matrix norm is, remember, the matrix, the original user item ratings matrix, but normalized, and you break that down and you get the U, sigma and VT. Once you get that, then you can directly, what this kind of gives you, sigma is the values, right, but not in the form of value. So this is a diagonal matrix. So diagonal matrix, by the way, if you are not familiar, which 20 cross 20 would basically mean that So diagonal matrix would basically have only the diagonal values, right? So rest of the values are 0, 0, 0. All of the values are 0 except the diagonal values, right? So in case of a 3 cross 3, this is what a diagonal matrix looks like. So basically all the values apart from your diagonal values are zeros. And what this diagonal and sigma basically gives you is the value of those the elements that are there in the diagonal. You have to kind of convert them into a diagonal matrix using this. Once you do that, then the making predictions from this is very simple. You basically, what you want to do is basically make the predictions of uh, you just multiply u into sigma and you multiply that into vt, plus you get user dot mean reshape, and basically you want to because add the corresponding means that you have subtracted to get, and once you do that you basically get the corresponding data frame of predicted ratings. And as you can see, these are the different predicted ratings for given users. So now they look like, so now if you have to make a prediction for user one, you know how to do about it once you have the predicted ratings, right? So this is the thing that I was mentioning earlier. When you're trying to make a prediction in case of in a recommended system, you're basically trying to predict the rankings of movies he has not seen. Once you're able to predict the rankings, then all you need to do is sort them in the order of the predicted rankings, and the one which has the highest predicted ranking are the ones movies which you will kind of which are the ones you will recommend to him, right? So that's exactly what you do. So for user ID with ID 0, you basically gonna recommend in the movies Return of the Jedi, Raiders of the Lost Ark, right? So these are the movies that have the highest predicted rankings. So that's about it. That's how SVD works. Now obviously there's a small part of it which I know you kind of did not get very clearly, is the part how we get the predicted data frame, right? So for that you have to understand SVD in a bit more detail. All we did was basically, once we decomposed our actual matrix, we basically recomposed it back. So we first decomposed it using u sigma dt, vt. Once we got u sigma and vt, we again then kind of multiplied u with sigma and then sigma with vt to kind of get the predicted dfs. And once we got the predicted dfs, then we got this. So now to understand that, I would request you to kind of understand SVD in a bit more detail. To understand why we exactly did that, but the procedure is very simple, right? So we take the matrix, we first normalize it, we break it down using SVD to into u sigma vt. Once we get the u sigmas and vt's, then we kind of again multiply them to get the predicted ratings. Once we get the predicted ratings, then we kind of sort them in the order of the predicted ratings to make the final recommendations. So now let's talk about evaluation metrics. So what are the different evaluation metrics that are possible out there? Well, because there's a predicted rating and there's an actual rating, so there are the ways to measure them are very simple, easy. The easy methods are one with root mean square error, which is where you kind of take the prediction and the actual rating. So what you want to do is basically, let's clear this up and understand. So you have got values, so you have got user u1, u2, u3, and you have got m1, m2, m3, and so on and so forth, right? And then basically you would actually have a actual ranking that they would have given, and if you now assume this ranking was not there and you try and predict a ranking, right, r hat, so using the way we have discussed already, so in those cases you can directly measure the r minus r hat and take the square, and then kind of for all the cases where you kind of there's actual rating present and you try and predict that, you get in a validation set, you can kind of take the difference of the predicted rating versus the actual rating, right? So I'm hoping this procedure is clear to you, right? So what you do is you basically first take out the validation set, right? Or probably a validation set could also be something like this, where you already know some ratings and those ratings you forcibly kind of hide, right? So you would already know rating R, but you would kind of hide it with a rating of 0, and then see what is the actual predicted rating of that particular movie, right? And then you kind of, once you do that, you would get the rating predicted. Now you actually had the R, and then you take the difference of R and R predicted, and you do this multiple times over, right? And that would basically give you a RMSE error, right? So R predicted is the root mean square error. Now there's also another concept of absolute error. Absolute error is something which is basically r minus r hat, and you take an absolute value of that, right? So that's one way. In this kind of RMSE or mean absolute error works perfectly in cases where you have actually predicted rating, and then you also have an actual rating of that movie, right? A lot of cases you might not have that. So this, what are some of the other ways where you can kind of measure, evaluate recommender systems is basically in cases there is a concept of precision and recall, right? So precision and recall is basically where you have this movie ratings, and then what you do is basically you kind of forcibly kind of take down the top 5 rated movies by the user, right? And you basically take the top 5 rated movies by any user, and you kind of forcibly make them 0, right? So obviously this forcibly making them concept is pretty something you're familiar with, right? And out of those top, say randomly top 5, some of the 5 rated movies you have randomly selected, this is not necessarily the top 5, you have basically just some random 5 movies that are rated highly by the movie, you have forcibly made them 0, and then you see that how many of those, then you also get the top, these are the 5 rated movies, right? So there's a list of 5 items, and then you also see the predicted 5 items for recommendation, right? So you basically build a recommendation system which basically gives you 5 recommendations. So that is like another list of 5. Now based on this you can basically calculate precision and recall, right? So recall is basically out of these 5 items that were there in the actual list, which were kind of blacked out for the recommendation system's performance evaluation. Out of those 5 items that were blacked out, how many 5 items, how many did actually get picked up? So that is a precision, sorry, that is a recall. And precision is out of the 5 items that were actually predicted by the recommendation system, how many were actually part of the top 5 rated movies that were actually there by the user, right? So out of this 5 predicted, how many are part of the list here, right? So that is your precision. And out of these 5 items that are there in the actual top 5 rated movies, how many were actually picked up by the recommender? So that's kind of precision. So those are recalls. So that's the idea of precision and recall in case of evaluation of recommender systems. And the final idea is that there's also some way of evaluating recommendation called diversity scores. So diversity scores are nothing very difficult to understand. Say in this list of predicted 5 recommendation systems, right? So one criteria that you also want to evaluate your recommendation system based on is basically how diverse are your recommendations, right? So if you're recommending say a movie from same genre, right, you basically figure out that this person basically likes movies from thriller genre, and you're just recommending him movies just from the thriller genre, which is also not a very good idea for a recommendation system, right? So what do you do in those cases is also something that you need to be able to understand. So as in, like, you need to be able to understand that you really don't want those kind of scenarios, and that's why what you do is you want to also measure a diversity score. So diversity scores basically measure how dissimilar basically your 5 recommendations are, or 10 recommendations are, right? So more the diversity, the better the diversity scores. So that's about it. So there are also a couple of other matrices also used for evaluating recommendation systems, but you have got the basic of them, right? The major one of them are basically mean RMSE, mean absolute error, in case you have a predicted rating. In case you don't have a predicted rating, you can still black out places and then kind of see if the precision and recall were high or not. So that's about it, evaluating recommendation. Now let's go into the next piece. So now we come to the final part of the lecture, which is basically something which is different from collaborative filtering. So as of now, we have talked about 2 broad concepts. The first was popularity based recommendation, the next was collaborative filtering. In collaborative filtering, we saw the user based, item based, then we talked about SVD. And now we are talking about final kind of classification, recommender systems, which are basically called content based recommendation systems, which is something which is absolutely similar to item based. In only difference from item based collaborative filtering method is that in case of item based collaborative filtering, we were basically kind of getting to that item similarity index matrix based on ratings of different users, right? If you remember, we had users, items, and then based on the ratings we came to the item similarity matrix. Now instead of doing that, what we are going to use is we are going to have information about the item itself, right? So in this case, movie and the rating and the year it was released in and the kind of actors, you know, all of those, the amount of money it collected in box office. So all of those can be basically different information about the movie itself. And for each movie, we would basically have this kind of information. Based on that, we can compute similarity between different movies. and use that to kind of get to the item similarity index, right? So if you remember this, for user item collaborative filtering, we basically had this kind of a matrix, right? M1, M2, M3, and then M1, M2, M3, M4, and so on and so forth. And then we had basically the U1, U2, U3, U4, and M1, M2, M3, right? So we had basically computed our item similarity matrix, and we had used, for doing that, we basically used the rows, the similarity between different columns, right? We had computed using this, and instead of doing that, so this was my Rx Ry vector, right? And instead of doing that, what we are now going to have is, we are going to have each of the movies M1, M2, and we are going to have different information about them, right? So feature 1, feature 2, feature 3. So this is information about the movie itself, right? And based on that, we are going to compute the different similarity between different movies and use that to fill out our item index, right? Item similarity index. That's the only difference. So there's nothing much to do about it. So once you understand, the rest of it is the rest of the flow is exactly same as the way we had done for it, right? Which is basically see which are the users, for every user for whom you have to recommend, see which are the items he has already liked. Based on those, you figure out what are the top 3 most similar items to those items, and once you do that, combine them all in a list, and based on that, you make your final recommendation for that user, right? So that's exactly same as what we have done in item collaborative filtering. So so now let's look at this particular example. The example basically has this data which has got different description of different IDs, right? So now our IDs are basically different items that we have right now, and we find that unlike other data sets that we have handled so far, we cannot easily, so this data set basically has got some description, so we can use that description to compute similarity between different items. But the problem is that it's not anymore similar like the way we had done earlier, right? So earlier we know how to calculate a distance between set of 2 vectors, right? So 2 vectors that are basically represented as, say, 1, 0, 1, right? 0, 1, 1. We know how to kind of calculate the distances between these 2 vectors, right? Similarly, if our features basically represent like 1, 0, 1, 0, 1, we know how to calculate the distances between them, right? So we know how to calculate a distance between them, Euclidean distance. But right now the problem is that for each item we do not have the features. We basically have a text blob, right? So how do we calculate the distances between 2 text blobs? That's a problem. So, but then that's not a lot of problem. Now that you have learned about NLP in the last lecture, you already know how to do this, right? It's very simple. TF-IDF, right? So what we basically need to kind of calculate distances is basically a set of features. And how do we calculate the set of features is basically very simple. You have to convert the text block into a set of vectors. That's exactly what we learned in NLP, right? If you remember, we talked about TF-IDF and all of those things, right? And you fairly know what all of this term frequency into inverse document frequency. So that's exactly what we are going to do here. So our feature 1 is basically a one particular token, feature 2 would be another token, feature 3 would be another token, feature 4 would be another token, right? And then we would get the count of that token and multiply that by inverse document frequency to get the TF-IDF for each token and each item, right? Each item is now a text blob, so we convert that text into a set of vectors. Once we do that, then computing the set of distances between them is absolutely not tough. So we have already talked about all of this. So TF-IDF is basically what we have term frequency into inverse document frequency. With this newly get, so what we do is we create a TF-IDF of matrix of unigrams, bigrams, trigrams. We have talked about unigram is basically one token is one word, right? And bigrams is 2 words are combined to make one token. Trigrams is 3 words, three consecutive words. All possible combination of three consecutive words are separated as different, are treated as different tokens, right? So that is what TF-IDF for unigram, bigram, and trigrams are. Then we basically compute the similarity. So once we kind of get that vector is representation, then the rest of the process is very simple. You kind of calculate the distances between them using whatever matrix again you want to use. And once you do that, you can very well easily get the rest of the process as well, right? So that's about it. So now in this case, we basically first convert them into an n-gram range of, so we use bigrams as well as unigrams, bigrams, and trigrams, right? We pass n-gram range equals to 1, 3, and then once we do this, then we use a cosine similarity to kind of calculate the different distances between different items in that particular row. Once we do that, we kind of then figure out what is a similarity item similarity matrix, right? So the first part is to take a text. So there are three parts to the process, right? First, text to vector, right? So basically, which is using TF-IDF. Once we have the vector, then this is the vector that we would have. So this is from here we have to compute similarity between different items, right? So m1 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 m2, so we have to compute that. So this is vectorized form to so item similarity, right? So vectorized form to item similarity. Once we compute that, that can be computed using cosine similarity or any other matrix that you do. Once you do that, the final process is then from here. The rest of the process is exactly same as what we had done in item collaborative filtering, right? So now so basically what we now do is basically get the different items that are familiar to the last item in this particular data set, right? So if we do that, we basically get all the sorts of items that are very similar to the last item. The last item was some box or shorts or something, right? And if you basically do that, you can. So what we did here is similarities and yeah, so now for every item you can basically get the corresponding item similar to that, and in this case we get the top 10 most similar item corresponding to this item, which was the last item on this particular list, right? So based on that, we can get the top 10 most similar items, and we can see that the top 10 most similar items was something like this. So that's about it. That's the entire thing that I had to talk about recommendation systems. So we have talked about what is recommendation system, the long tail problem of those sorts. Then we talked about most popularity based recommendation system, and we talked about why that is not the best of approaches because that kind of lacks personalization. But then we also talked about the fact that hey, that's true, that lacks personalization, but then there's also something that comes out of it, which is basically the fact that a lot of times when you want to don't have user history about the particular user, right? He's completely new user, or he has probably not logged into the portal. In those kind of cases, you want to showcase something to him, right? In those cases, you can use popularity based recommenders. In other cases, for example, if you have breaking news or anything of those sort of cases, right, where you know that the most popular item is the reason why people are coming to your website, so in those cases you also might want to use popularity based recommenders. Hey, that's one story. Now then we talked also about collaborative filtering, which is the most widespread used approach ever, right? So in that case, we talked about user collaborative filtering, we talked about item collaborative filtering, then we talked about the problem of sparsity and how that can be kind of circumnavigated using SVD, where we kind of use genres to represent movies instead of representing each movies as different columns, right? So we compress that representations, and when we do that, we kind of, after we did SVD, we talked finally about content based recommendation system, which is absolutely similar to item collaborative filtering. The only step is we do not use the ratings to kind of infer what is the similarity between two items. We use the actual item and their corresponding attributes, right? So for example, movies, we will use the different attributes over the movie itself to kind of compute similarity between two movies. In this example that we basically had items which were basically different text blobs, right? And we had to compute the similarity between different items. So what did we do? We basically first converted the text into a vectorized form using TF-IDF, and then it was simple. Once we had a vectorized form, then we could take cosine similarity, and when we took cosine similarity, then we could compute the item similarity matrix, right? And that's about it. That's everything that I had to talk about our recommendation systems. Though there are a couple of other things which are very important, and those are something that I would definitely recommend you to kind of have a look at, which is basically what are the different problems associated with the recommendation systems, right? So cold start and the trustability issues. So those are some of the things that I've referred to in the extra additional material out here. Have a look into them. But that's about it. That's a wrap from my end. I hope you enjoyed the entire recommendation lecture, starting from the entire machine learning part that I've been talking about all the way to recommendation lectures. I hope you enjoyed the entire lecture. I hope I have been able to add some value to your learning process. And I hope GreyAtom as such has been able to kind of add value to your machine learning understanding of machine learning. With that I would end the lectures. Hope to see you soon.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.